Good day class. Today we will be trying to cover what are the different spectral property of any given signal. It can either be a periodic signal or an aperiodic signal. So let's first look at the spectral properties of an aperiodic signal. So we look at three different cases. The first, that your signal is real, it's real and even, and then finally we look at if it is real and an odd signal. So the first thing is, what do we understand when I say that my signal is real? What that means is that the x conjugate of t is equal to x of t. Why is that? Because the imaginary component is 0. So the real the conjugate of your this signal is going to be same as whatever your original signal is. So if that is the case, the corresponding Fourier transform relationship becomes that x conjugate of f is equal to x of minus f here. And based on this, I can figure out the saying that magnitude of x of f is equal to magnitude of x of minus f. This means that my magnitude here exhibits even symmetry. While if you look at the angles, I can say that the angle of x of minus f is equal to minus of the angle of x of f. So this correspondingly represents some form of odd symmetry. Let's try to understand this better by using an example here. We are given this Fourier transform pair x of t is equal to exponential of minus 4t u of t, and the corresponding Fourier transform is 1 by 4 plus j 2 pi f. So let's try to plot the original signal x of t and the corresponding spectrums here and figure out how if these properties are valid or not. So let's first plot exponential of minus 4t times u of t. Since it is multiplied with u of t, I know it's only going to exist after t equal to 0. So then I'm going to have something like this. I'll have an exponentially decaying signal here, and this is going to be my x of t. We will be plotting the spectrum of this signal here in two phases. The first would be your magnitude spectrum here, and then we will plot the phase spectrum here. So if I am plotting the magnitude spectrum here, something like this here, where then this continues on to become 0 at a specific point of time. The phase spectrum of x of f would be something like, where now these values here are pi by 2 and minus pi by 2 here. So let's look at these waveforms and see what we understand from this. If you look at the magnitude spectrum here, you can see that it has even symmetry here. If you look at your phase spectrum here, we know that it has odd symmetry here. So if you don't know anything else about x of t apart from the fact that it is real, then we can say that the corresponding spectrum of the signal is going to have even symmetry for the magnitude and odd symmetry for your phase spectrum here. So the next thing we look at is if x of t is real and even. What that means is that my x conjugate t is equal to x of t, while x of minus t is also equal to x of t. So these two conditions have to be satisfied, so that only then my signal can be called both real and even. The corresponding Fourier transform relationship is that the x conjugate f is equal to x of f. What that means is that this signal is also real, because now since the conjugate of the function is the same as the original function, I can say the signal is real. And the second relationship is that the x of f is equal to x of minus f, which means I am going to have even symmetry here. Let's take another example to draw out the x of t and the corresponding spectrum for that x of t. Let's take the basic signal rectangular function rect of t. So that's going to look something like this here. Now we know that the Fourier transform of a rectangular function is a sinc function, which is going to be something like this here, where this corresponds to your frequency here. Now looking at this signal, so this itself here, we know that it is a real signal. There is no j term involved, or there is no j term or e raised to j5 with your sinc function here. So we know that is going to be a real signal here. If you look at the spectrum of this signal now, x of t, you can say that this has even symmetry here. The third condition is if x of t is real and it is odd. So what that implies is that my x conjugate t is same as x of t, but x of minus t now is equal to minus of x of t. The corresponding Fourier transform relationship is that x conjugate of f is equal to minus of x of f. This will only happen if my x of f is purely imaginary, which means my x of f here there would be no real term, but only will have imaginary terms, or will have something always multiplied with j to it. And the second relationship is that the x of minus f is equal to minus x of f. This gives me odd symmetry. So let's take a signal which is real and odd, which is 1 minus of 1 by root 2 pi into t into exponential of minus t square by 2, and the plot it and see what we get here. So this signal here correspondingly looks something like this. So this, by looking at the signal, I know that this is a real signal and I know this is an odd signal. The corresponding, if you look at the Fourier transform of this signal, we can see that x of f is now j 2 pi f into exponential of minus 2 pi square f square. If you notice this, there is this j term which is present in this whole of x of f, which means that my x of f now is imaginary in nature. Let's plot this imaginary section of x of f. So if you look at your x of f now, this again also has odd symmetry. So this is a purely imaginary function now and it has odd symmetry. So I can conclude that if x of t is real and odd, my x of f is going to be imaginary and is going to have odd symmetry. Similarly, if my x of t is real and even, I am going to have x of f as a real function and it is going to have even symmetry. And if I do not know if it is whether even or odd, and I only know that x of t is real, then I know that the magnitude is going to have even symmetry and the angle is going to have odd symmetry. So this was specifically for aperiodic signals. What about for your periodic signals? You do not have continuous waveforms there, you mainly have coefficients, Fourier series coefficients. Because we are dealing with periodic signals now, we will be using xp of t. If my xp of t is real and I do not know if it is whether even or odd, then again my magnitude is going to have even symmetry, which means xk here and x of minus k would have the same magnitude. So this will have even symmetry and correspondingly the angle is going to exhibit odd symmetry. So if my xk angle is positive, say pi by 2, my x minus k angle is going to be minus pi by 2 at k equal to whatever value we have there. So this is going to have odd symmetry. The next is if xp of t is real and even, then my x conjugate of k is going to be equal to x of k, which means I am going to have a real signal here. And finally, the next thing is that the xk and x of minus k have the same value, which means I am going to have a even symmetry here. And next, the final thing is if xp of t now is real and odd, for example like a sinusoid, a sin omega t or a sin 2 pi f t, then I can say that the x of k conjugate is going to be equal to minus of x of k, while my x of k is equal to minus of x minus k, which means this happens only if my x of k now is imaginary and this would imply that I have an odd symmetry at my coefficient here. So x of k is going to be equal to minus of x of minus k. What that implies is that, so if x of k at k equal to 1 or x of 1 is 1, then correspondingly x of minus 1 is going to be minus 1 here. So that is what this effectively means here. So you can use these basic ideas for your spectral properties to verify if your answers, if your questions, your spectrums are actually correct or not. Because if you know that, for example, your signal is an aperiodic signal which has which is real as well as even, then definitely I can say that I am going to have the Fourier transform also to be a real value, and the Fourier transform function is going to exhibit even symmetry. Another way is if you are given the spectrum of a signal, let us say you are given one of these spectrums, you can figure out what type of signal you have. So if you are given something like this, I know my signal is real. If you are given something like this here, I know because it's a real function as well as it has a even symmetry, I know this one is going to be a real function and an x of t is going to be real and even. And if I am given something like this which is purely imaginary and has odd symmetry, I know x of t is going to be real and odd.